Okay, for people joining this live stream, we are starting to look at some functionality for the upcoming version of Wolfram language. There's always an upcoming version, but as they get closer, we look more intensely. There will be a whole bunch of these design reviews coming in the next week or two. This is our very first one, and it is on the subject of calculus and algebra, back to some of our earliest killer features. All right, start off. Special functions, foxh. Is this the first time we've had foxh? I thought we'd had foxh before.
No.
Wow. But people have been militating for foxh for years.
That's right. And no, we're gonna get it.
Who was Fox anyway?
Charles Fox. He was I think he wasn't the biggest contributor to foxh, actually. I think that the precursor to all of this is Melan and Barnes. So Hjalmar Melan, or Melin, he's han är svensk, he's Swedish, Swedish Finnish. And then Barnes is a British guy who became a big wheel in the UK church. So he left academia. But they studied something called Melan Barnes representations that are basically these kinds of integrals of gamma functions that you see there.
Yep.
And Mayorg, which was introduced in version 3 of Mathematica, is just slightly simpler than this. If you look at those gamma functions there, what's new here are all those alphas and betas. Those are just one in the case of Mayorg.
Wow, and that's taken 25 years?
So this is getting closer to complete Melan Barnes, everything that Melan Barnes can represent.
Why are we showing off with some weird thing here? We shouldn't do that.
No, it's not final. Sorry.
Okay.
We won't.
Well, we're going full Swedish here with Mitta Leffler as well.
Yeah, Mitta Leffler is the actually the advisor of Hjalmar Melin, and Mitta Leffler was a PhD student of Carl Weierstrass.
Okay.
And he's the reason why there's no Nobel Prize in mathematics.
I know that story. Yes, I know that. Is that story true, or is that?
I don't know. It's probably not. Probably just a good story.
Okay. So basically,
this thing is kind of a useful representation, just as Mayorg has been a very useful representation for doing like definite integration, because when you have products of things, it becomes a type of convolution in this space, and it becomes very easy to do the integrals. So this generalizes this. So this extends the scope of what can be integrated. It's heavily used in probability and statistics for distributions. That's one area where people have gone through all the trouble of
what's the characteristic integral that can be done with this?
It's sort of products of things, products of hypergeometrics.
I see. Okay, cool. Anything we should look at with respect to this? It seems like it's a fairly straight shot.
Yeah. So we want to introduce this as experimental because we are not entirely sure that we'll get all the evaluation and all the support in time for 12.3. And then we expect to unexperimentalize it in 13.
Okay. Carlson elliptic integral functions. That's a lot of functions.
That's right.
Okay. Should I pick a random one?
Yeah.
What are the R and the F? What do those stand for?
The R is the general Carlson R from which all these are derived. And then the F's, etc., stand for first elliptic integral, first kind, etc. So roughly speaking, the F is first elliptic integral, K is the complete elliptic integral, etc. So they are related to the current elliptic integrals, but they are definite and not indefinite integrals. And they're symmetric. So you've got two parameters, X and Y, or three, and they're symmetric in those parameters.
And we really need all of these guys as separate functions. I mean,
Well,
look, given that we've got Jacobi CN, Jacobi whatever, I don't think it's cognitively difficult to have a lot of these functions. It's just kind of weird.
yeah, I think that they're actually even more in DLMF. So
Yeah, there are 10 and we picked 8, which looked like they were not redundant anyway. So, but we need them because they are going to be output from integrals eventually. And it'd be nice to have clean names for them for each separate one.
All right. Okay. Pockhammer.
it's basically kind of like a bug fix to correct asymptotics or better asymptotics.
Okay. Okay. All right. Let's get into some meat here. Okay. Where? I mean, just get me some scope for this design.
Yeah. So there is. Let me just. Yeah. So let's talk about the algebra. There's a couple of very exciting things there. So for optimization, symbolic optimization, there are two things. One is to do what's called parametric optimization, and that's when you have parameters in addition to the decision variables.
Yes.
We could already compute some of that using cylindrical algebraic decomposition.
Right.
But we have now a new method that allows you to give both better result and really scale to solve fairly big problems. This will go directly into something I'd hoped for its release, but it will make it for 13, which is something called model. It will be used many applications, but here's one. It's called model predictive control. It's a fancy, modern, advanced control design scheme. So we'll talk more about that in the future. So this is already going in there. The second big thing for optimization is pretty amazing, which is that we are able to solve everything that we can solve in convex optimization exactly.
Wow. Okay. Which you can also do for linear programming can also be done exactly if it can be done, right? If the simplex method can do it, you can.
That's correct. Now, there are, of course, some barriers, because of scale, because the numeric case can still go up higher. But part of what we needed to do, without going too much into the details, is that at the optimum, because for convex problems, we know the dual variables, the lambda and the mu variables for the dual problems.
Yeah.
That means that we also know what are the binding constraints, or what's called the active constraints, the ones that are equalities, equations. And so we have sorry?
My question is, I mean, when you go to the corners in a piece of convex optimization, when you go to the corners in linear optimization, you're just going to get rational numbers.
Yeah.
When you go to the corners in convex optimization, what do you get? Do you get algebraic numbers, or what do you get?
Yeah, whatever is in the problem. So it might be worse than algebraic numbers. They're transcendental numbers often.
But we can represent them symbolically.
Yes. So the big innovation here, what we needed to represent is the symbolic solution of a system root.
Yes.
Okay. And so since we know where they are, we can verify that it is a unique root. That's what we know from convex. It's the unique global thing, and it's a unique root. We can now validate that independently once we have a good enough approximation to it. That means that we can raise the precision to infinite precision from finite precision.
I see. So you have a way of describing a root for a system of equations.
That's right.
You can describe a specific root by some indices, and you can validate that those indices are sufficient.
That's right.
What happens if it's a non-trivial algebraic variety that is the solution?
Well, there are cases where when you have multiplicity, that it may not work. For algebraic varieties, we in principle could always figure that out. For analytic or locally analytic varieties, it's a little bit more dicey. So actually, I think it's root new that has the updated.
Okay. All right.
Yeah. This one has a little bit more work to be done on it because we're going to build illustrations there and things. They're just prototypes of things.
I see. What is the root ordering method?
There is an old root ordering method that was introduced in version 3 of Mathematica, and it sorts them, and so you can use an integer index to indicate which root.
Yes, but that only works in the complex plane. Yes.
That works when you have only finitely many and you know globally all of them.
Mm-hmm.
It doesn't work so well when there are infinitely many and you don't know globally all of them.
Mm-hmm.
I mean, it cannot work then. It's just the idea is not good enough.
Okay, so what's the approach?
So then the other approach, we use a neighborhood of the root that guarantees that there is only one root in that neighborhood.
What's the shape of the neighborhood?
It's a multi-precision number with where the precision tells you the radius of the ball.
So it's a ball.
Yes.
In the complex plane.
Yes.
So in general, it can be multiple complex numbers. So it's a ball in the n-dimensional complex space.
Yes.
Okay. And precision doesn't mess you up.
Actually, strictly speaking, I think it's a polydisk. But
precision doesn't mess you up at 0.
Well, then yes, then it has to use accuracy. So we haven't really described all that yet. There, we have more iterations to be done on this. I'm sorry about that. It just got delayed.
Okay. All right, but basically the description is. Which one is it here? Near x equals c.
Yes, that's the second one.
Mm-hmm. Okay. I see. Okay, how does it? I see, and it knows how many variables there are. It just counts the number of equations.
Yes.
And it's always the number of equations is equal to the number of variables in all cases.
Yes.
Okay. What design issues are there in this section?
There's none really. I mean, there is the new thing that was you actually asked for it, which is solve values and end solve values, which we had some discussion over email over the weekend, just briefly. And that's just basically they're more or less the same functions, but they have different output structure.
Yes.
To simplify workflows like for plotting and other direct uses of.
What happens if it only has one? So it's always going to give a list. Is that correct?
Yes.
So if I say solve values of ax plus 1 equals 0. Oops. Oops. That wasn't what I meant. I see. Okay. And it's pretty obvious what it can do. If I were to say
this is what solve does. When it parameterizes the solution, it uses one of the solve variables as parameter, like x in this case.
Okay, so with a single variable, these inner things are just singletons.
Yeah.
Okay, makes sense. Okay, and then solve values does the obvious thing. Okay.
Right. So one more thing introduced here now, because we have these systems, by the way, is to be able to solve transcendental systems of equations in a box.
Okay.
So behind the scenes, this is using a new type of interval methods and so on. But it was the machinery that we developed for this other optimization case that it caused us to. Get the
Okay, so wait a minute. So this is what I should look at. Yeah.
Yeah.
This is
These are really nice, these multi-parametric linear and quadratic programming.
so min value. Hope there's a simpler example than this.
Yeah, you can make it as simple as you want. But it still needs to be sort of linear and quadratic programming or something transformable to those classes.
Right. Okay, cool.
This can be done much simpler. I just ran out of time.
Okay.
Here's a much simpler way to formulate this. But basically everything convex.
Okay, so listen, I want to talk about these things, okay? I want to talk about how you use these, right? How do I get out the minimal polynomial, for example?
First.
Okay, I'd never know that. I'd never know that, not in a million years.
Okay, we will describe this in the new root object.
Okay, but it's not just a description. I think in modern times, I mean, so what else can you get out of here? The numerical value, I understand how to get that. That I'm not confused about. So if I
but
say,
it's more than the minimal polynomial. It's a function. It's generally a function. Sometimes it's a polynomial, but now you get out a function.
But it isn't just a function. It's full of crap here.
Right.
So that's not just a function.
Well, it's a system and it's approximation. Yes.
Yeah, right. Which is a different thing.
Mm-hmm.
So I'm going to come back to my same question. I want to get out of here. I mean, I understand it has all this stuff packaged in it. I'm just saying we need some kind of accessor, and we probably need, some kind of Raft or autocomplete or something that allows you to just extract the thing you need out of this.
Yeah.
Like maybe it's the minimal polynomial, but I don't even know whether that's, it's this.
I mean, we can easily support a bunch of properties for it.
What happened here? What happened here? Why is that reddening up?
What
the heck? Maybe it's just some bug in the prototype build. I don't know.
Oh, yeah. What?
Okay.
I'm still confused.
It's very confused.
What?
Well, something is very wrong here.
Oh, look at that. They're two separate functions. It's not a, you put the break. Okay, so there was a vector of two functions.
Yeah, well, fine. So, I made my points here.
Yeah.
It's a mess, right? Mm-hmm. You got to be able to have a better way to get these things out.
Okay, we'll fix that.
What does it do if I say normal?
It is normal already.
Okay, so it's going to do nothing.
Yeah. Input form will display the input form.
Great. In all its incomprehensibility. All right.
Right.
We need some way to access things from here, and we need it to be visible in this mouse over in a more useful way than this is.
Mm-hmm.
And by the way, if you're going to do a prettified mouse over, then you should just put X's and Y's in there for that first, thing rather than the hash business. Yeah, I mean, this is not right. This isn't right. What you have for the mouse over and things there. The results are impressive, though.
Yeah, this is the transcendental system in a box.
It's impressive. I mean, I guess if I say here, Lovely. There's something that bothers me about these. Maybe it's a graphic design issue. Maybe these numbers just shouldn't be in code font. Maybe they should be in text font. I think that would help. Because
I tend to agree with you.
The thing is that this makes me feel like I can get that number out somehow, whereas that number is just a label. Do you see what I'm saying?
Yes.
Why don't we ask design, but I would suggest just changing that to text font.
Yeah.
Because the things drive me crazy. It's like, I want to pick that number up, copy it, do something with it, but I can't. But I do feel like, on hover, there should be some kind of raft that gives some options,
When you say raft, I'm thinking of something that floats in a river.
Yes, that's what I'm talking about. I'm talking about this. This is, let me show you an example of that's a raft, whatever you call it. That thing there that floats underneath it.
That's a raft? Okay.
We're calling that a raft. That's our UX name for it.
Okay.
Because it floats, it's a kind of it helps the user. It's like a lifeboat type thingy, but it floats. That's why we called it that. I'm surprised you haven't heard that term before.
I've heard it, but I'm never sure what it means, because it seems like we made it up ourselves.
We did make it up ourselves. It's a floating UX element.
Okay.
It's a floating assistive UX element. Okay, and I'm suggesting a raft here rather than that tooltip, which is not very useful. I'm suggesting a raft. This raft actually does something. It can go pick that up, right?
What would the raft do?
I think it might give you some options for what you can pick up from that thing. I'm not sure. It requires thought, okay? It requires knowing what you can do with this. I mean, one thing is give me the numerical approximation. Another is, give me the minimal polynomial. I don't know exactly what.
Yeah. We were talking about sort of having a click. So these need to be smaller than our big summary boxes, which are massive, and you typically only have one per line. But here they'll be in formulas, lots of them.
Yes, I know. I think it's fine. I think it will help a lot to change that to text font, because that will look more like our entities, where you're not expected. It's not like you can pick it up and copy it.
Right.
Okay, let's keep going. Find instance. Wow, that's pretty cool. That's pretty seriously cool.
Yeah.
I mean, I assume that what is the for example, what is the sorting guarantee for these guys?
Sorting guarantee.
Can I sort them?
Yeah.
And if, for example, if I say, okay, so let's do this. Let's say integer part.
Yes.
Pretty nice. If I say fractional part, I'll get some, presumably. Yeah, pretty nice. Okay. And so what about canonicalization?
It is canonical.
So equals will work.
Okay. Yes. I mean, but it won't do. It depends on what you mean by works. Equals work if they are the same within numerical. No, they don't. Sorry. No.
Yeah, because in general, your bounding box, two
No. It's not like approximate number. These are exact numbers, so it's not.
I'm aware of that, but my point is their representation, their bounding rectangle or whatever, they might represent the same numbers. Clearly, there are multiple ways. By the time you're in the transcendental domain, it's undecidable whether two things are equal, right?
Yeah, but if they satisfy the same equation, and you have balls that are, let's see, if you have balls that are, yeah, if one ball is included in the other, then, you know, both of them guarantee there's only one root, then they have to be the same.
Okay, but I think there's a little bit more to say about this, because I mean, you can clearly have two different representations. You can have representations with zero, or is that, will you detect that by the numerical evaluation? An ornate definition of zero in terms of, you know, nested trigonometric functions that might be difficult to prove as zero, you might still detect as zero, or not.
No, I don't think this can solve the general zero equivalence.
Well, it can't, because it's undecidable. General zero equivalence for trigonometric functions is undecidable. So you're not.
No, you need absolute value as well for that to be undecidable.
Are you sure?
Yes.
That you can't do it with trigonometric functions alone?
No, for trig, no, trig alone, it's not. You need something else, like absolute value is usually what's.
Okay. Well, okay, but in any case, but I mean, I can clearly give. So, can you deal with absolute value in these transcendental root objects?
Yes.
Okay. So, I mean, but you might be able to break out of the undecidability by just doing numerical evaluation.
Yeah, for many things, but in practice, for most things, it's not an issue. But will there be boundary case? There will be boundary cases where just.
So I'm asking you again, in double equals, the you know, what are we doing with double equals in cases where, is it going to return false incorrectly in certain cases?
No, I don't think so.
Okay.
If we had Adam here, we could answer your question.
Why don't we try and get Adam?
Yeah. Someone contacted him?
Yeah, I'll ask. Okay. All right, let's keep going. Construct a system of root objects. What does this mean?
What? Well, this is what we spent a lot of time talking about already.
Okay.
This is slightly different. This is more domain knowledge about elliptic
This
functions.
seems like Adam's stuff. Maybe we should wait until Adam is here.
Yeah.
Okay. Let's go talk about, did we have a permanent before?
Yes.
Yes, we had it, yes.
This is an improved performance.
This performance, yeah.
But what's the default method? Because that's all we care about.
Yeah, the default method, yeah, is the one right on the third one. Yeah.
But that's no, well, I mean, but no, why? Okay, come on. You know, we got to be able to figure out, when should we be using these methods? Okay, because that's what makes a method valuable to us, is when it gets used by default, not when, I found it in documentation and somebody told me about it, you know, once.
No, look,
rumor.
You have no argument for me, okay? This is Dan's work. If we want to,
okay, then get him here. This is what we need for these meetings. I mean,
we shouldn't have brought this up here.
Okay. Who's QR decomposition?
That's Danny as well. Yeah.
Okay. All right. Let's go on to the next item, and we'll wait for Adam and Danny to get here. Otherwise, we'll loop back and talk about their items in another meeting.
Sure.
Okay. Bilateral Laplace transform.
Right.
What is that?
That's just the Fourier transform extended to the full complex plane.
Or it's the unilateral Laplace transform extended to the negative real axis.
Exactly. Yeah.
Okay, listen. I've told you this like 75 times. Why is that if still in that stupid font? Come on.
Let's get Itai here too, so we can have this hash this out here for sure.
Okay. That's not staying like that. Why is it still like that in this version? I thought we agreed to fix it. Okay. What can we look at that isn't we're asking for?
This has nothing to do with this review, the typeset font there.
Okay,
but well, we'll discuss it. We'll cover it.
Yeah, we need to cover.
But this is bilateral Laplace transform.
Okay. And why is it in a box?
Because it's a conditional expression.
Right.
Okay. I think it should be a gray box, not a black box, but anyway. Black box has sort of bad connotations.
Right, yeah.
Okay, I don't really understand what this thing is, so maybe I should just run a particular, I mean, if I just say 1 over t squared or something.
Oh, I just got a singularity at 0, so I guess that's a problem. So
it took a very long time to decide it couldn't do that.
Right, this goes to integrate because it requires generate conditions. I mean, the best one that will work are always the bounded support, like unit triangle, something like that. That should be.
Hey, why is this so unbelievably slow?
Because it relies on integrate, and we need the conditions. If we didn't, we'll have some special method maybe, but we do require the conditions over here, and integrate unfortunately is very slow for them.
I'm going to ask my question again.
Yeah.
In a very elementary case like this, why is there not tons of stuff we can cache to make this not so slow?
We could do some table lookup. Yes, we could do that.
Seems useful to me because this is pretty dead in the water.
Yeah, right.
Boy, we got some modern people on our live stream. Somebody's asking, can you get that colorful graph as an NFT? Yes,
so
we are thinking as a non-fungible token. Yeah, as like a CryptoKitty.
Oh.
It's become the craze the last few weeks, and we are actually in a very good position to support those things. So
that was a.
What's that?
Okay, yeah, that's an interesting request.
Okay, so I'm a bit disappointed it's so slow. Is there anything for which it's not slow?
Unfortunately, the direct one it's not so slow if you got things like which are piecewise, which tends to be a bit faster. If you got a piecewise, like which or it's got only half.
No, but why is this? I mean, like if that instead of k there was a 1, for instance, there's no parameters, shouldn't be a problem, right?
Yes, I said that we need the conditional expression. That the problem with table lookup, in a special method, conditions are a bit hard. So basically, we have to rewrite integrate for this case. So
yeah, this is really pretty awful. If real part of s equals 0, what about if real part of s isn't 0?
Well, this one relies on the current legacy integrates. That will be replaced eventually, but that's what we have right now.
So what are we achieving with this?
It's been requested many times in the last couple of years by people from signal processing, basically, and they want us to, because they want the conditions and they want us to, on the inverse, they want the unit step to show up. So when you do the inverse of a bilateral Laplace transform, you get, so
the inverse bilateral Laplace transform?
Well, if you do, let's say you do, the hard part over there, so let's say the first example, right, you have a rational function, okay?
Okay, sorry. I just found a bug.
Oh, sorry, yeah, that's a bug. I'll just note that. Yeah. So if you do a rational function, okay, and you do the inverse bilateral Laplace transform, then that's the case that interests them. They want us to be able to do that correctly with the, the strip of convergence.
Okay.
Yeah.
Okay.
Yeah.
Right. Well, I'm not impressed in terms of speed, but.
Yeah. I don't think there's much. We can do a little bit, but not much in this release and speed. long term, the new integrate will solve a lot of it.
Yeah. So the first example took
Okay.
0.4 second, 5.2. Now it takes 17 seconds with the same integrate, same example. So we lost 45%, 45 times. Sorry. Anyway.
Lost it for what reason?
Yeah. Well, for what reason?
Well, because I didn't maintain, but it's just that people have been maintaining it, and it's just had so many bug fixes over the years, thousands of them, that now it needs to be just replaced, basically. So.
Which thing are we talking about here?
So things like, particularly when you got the full real interval, then integrate has a rough time because it needs to do the two separately and then combine them. That's where it gets in trouble. It's not so bad in the Laplace transform itself. The bilateral is on the whole real line. That's what causes problems for it.
Okay. Well, it's a bit unimpressive. And I think it could do with a bit of profiling before you wait to the infinite future for replacing everything.
Yes. No, but I think we'll certainly make some improvements for sure.
Okay, look, I have a procedural point, which is that, can we please make sure, I know we have a lot of these design reviews coming up, Roger, let's please make sure that everybody whose functions is being talked about.
I mean, you wanted to drill in more, and you go on tangents, and that's going to require many more people.
Well, they should be on call. Anybody whose function is being discussed should be on call.
I think that's fair. That's reasonable.
There. Okay.
Okay, I'm here. I apparently was requested.
You were. Why is this still in the ugly font?
Because I'm waiting for whatever other updates design gets me and putting them in all at once.
Okay, fine.
And
who is working on that?
Billy, and I got an email from him a couple of hours ago that he has something for me to look at, but I have not had a chance to look at because I've been in other meetings.
Okay, fine. All right, okay. But so we had agreed that we had agreed on what this roughly was going to look like, right?
I think so, right? That you wanted a slightly lighter
that
frame.
font, the if cannot be in code font. That's the main thing.
Yes, and I don't know which particular, right? We have more than one text font, right? So I don't know which.
Okay, fine. But he's dealing with that.
He's dealing with
and
that,
this
yes.
frame should be lighter. And other than that, that's the basic story here.
Yes.
But this is the most important thing. That this is reading like code, and it's not code.
Okay.
Okay.
And you reported that, and like I said, I'm just waiting on the final spec from design instead of putting in a half measure.
That's fine. That's fine. I mean, if that isn't done by the time of the design UX meeting at the end of this week, then please complain.
Okay.
Okay. All right. Was there anything else for Itai here?
No, I mean, the root object's going to be for him too, but if you want to go there.
Well, the root object that's a whole story about putting rafts on root objects, but I think you guys should talk about functionality before we have a conversation about look.
Okay.
Okay. Thank you, Itai.
Okay.
Okay, let's keep going down here.
There's no design change. This is new capability. It means that linear equations with basically rational functions of trigs and hyperbolics and exponentials.
This is using differential root.
Yes.
Yeah, it doesn't have to. If it's low order, it doesn't necessarily use differential root.
You know, I got to tell you something, guys. Sorry.
We should bring in Itai again if you want to have that discussion.
Okay, look. In this case, it doesn't do anything when you click. In the other case, it does something.
I know. I have had the same discussion with Itai.
Okay, then why don't we?
And it's, I mean, there's a reason for that. I mean, right? The difference is that the size of a typical differential root object is much larger than the size of a typical
all right.
normal
the problem,
root object.
the problem, and I don't want to get into this in great detail here because we've got some other things to look at here. The basic problem is that I, for example, got just really, it's like, how do I get this data out? I can see it here.
You select it and you copy it.
From this?
Yes.
From here?
Yes.
Oh my God, I had no idea that worked. Okay.
Well, why would you expect it not to work? I mean, it's not
here. How do I do it
it's not
here?
a tooltip.
Okay, but then why don't we make this not a tooltip as well? Well, if we had this be the same behavior, where look, presumably this had a hover,
which says click for more info.
I think that hover could just light up this D thing, because I think that would make it clear that you can click it without having to have the ugly.
I think that's a really
word.
good idea, actually.
Right, and then you click it, you get this thing, and this type of pane is not one from which I would have expected to be able to copy, because it looks too much like a tooltip. You see what I'm saying?
Okay. Right, and there's all right. Well, I mean,
I didn't figure that out. So just to be clear, you might just accuse me of being really dumb about this, but I didn't figure that out.
Okay, so let me right. So this is another thing that Billy is currently looking at, and I mean, I can put his mock-up in the chat if you want to look at it.
Yeah, sure, please do that.
All right.
Yeah, I think all of these things. Okay, so first point is this should not be in code font. This should be in some kind of texty font or mathy font or traditional form font or something. This thing here, because it gives one the idea you can copy it, which you can't. And so this will then light up, you press it, you get something here, which is more of a form where you can readily see that this is like a sub notebook where you can readily, with white background or whatever, where you can just copy things. Okay. And I think these should also have, let me make the comment. I think this should have a click to copy type. This should have click to copy iconography.
So each thing should have a button,
possibly, but I'm not sure. Well, on mouse over it should have click to copy, but the other possibility.
Well, I don't know that it should, right? I mean, what if you only want to copy out part of it?
Part of this.
Yeah.
Well, that's not an unreasonable possibility. I agree. What about the possibility of copying everything into a multicellular, input?
That would be kind of weird, right? I mean, you could achieve more or less the same thing.
Actually, what you really want is a list. That's what you really want. You really want to copy this out as a list, because that's what you want to feed into RSolve or whatever. That was the thing that was driving me absolutely up the frigging wall with what the heck are they called? The things that give you recurrences. The things where you have a
find linear recurrence.
No.
Difference root?
Difference root. Yes, difference root. It's driving me crazy. I want to get the stuff out of a difference root that I can feed into another function. How do I do it? Answer, I want this stuff as a list. Okay, if I go here and I can copy the whole list, right? That will be very convenient. In fact, I don't really understand why this is showing up not as a list here. I mean, to me, something formatted as a list with perhaps on different lines just for readability would be the best thing. Am I making sense? Because that's what I want most of the time, is the list.
Most of the time you will get the same object back when you feed it to RSolve or DSolve.
Well, fair enough, but I want to do things with it, I don't know what I want to do with it, but I want to do something with it.
Okay.
I want to go ahead.
Sorry, I was having trouble finding the chat button. I'm managing too many windows on screen. But there, I just put Billy's mock-up on.
Okay. Well, I don't like. Yeah, I mean, that's too large and bold, but that's okay. That's good to distinguish this, but then I don't think this is the right form. Yeah. Okay. Pop out, copy all. What does pop out do?
I'm not sure. Maybe it's copying that grid into an input cell, which I'm not sure would be particularly useful, but maybe if you want
this
to
is going to require further design. review.
All right. I'll just add it to the, well, if we'll have time, I'll try to add this to the LCC meeting.
Fine. But then what we need is all forms of box like this, please, together. And we need their behavior to be consistent between the algebraic root one, differential root, difference root, etc.
Okay. I mean, well, up to a point. I mean, I agree that algebraic number and root should be pretty much the same, and that root, that differential root and difference root should be pretty much the same. I'm not sure. Right.
Let's review it. I think they should be very similar, but whatever.
Yeah. I mean, just right. One is a representation of a number, and the one group is a representation of a number, and the other is a representation of a function. I mean, I understand,
and that's the difference. But the difference, the fact that one is a function and one is a number, should not be manifest in one being a tooltip and one being a pop out.
No.
Yes, I agree with that.
I think that we are at this point now where we can have this discussion. Before, we were just annoyed when they came out. Now they're small, nice. We want to tune it a little bit so that work for post workflows are.
Yes. All right. And yeah. Billy also needs to remember to design what they look like before you click. Okay, let's quickly go through the other stuff. And Itai, you're welcome to stick around for a couple of minutes. But what is ONT?
That's an old new function. I think we introduced it sometime 8 or 9 or something like that. But anyways, what this does, it solves systems of differential equations with rational function coefficients. And it's complete. It can solve every such system.
In terms of how exotic functions?
Well, it will eventually need differential root.
Yes.
I see.
Because, ultimately what it does is triangulate the system to, so you get a single ODE. You solve that, you back substitute, and you get to other ones.
One day it will be lovely to have some kind of essay about what the heck the point of this.
We will.
Okay.
You will have a lot more useful information. I think that the information in an appendix style was a little bit on the terse side.
Indeed. That was 30 years ago, though.
Yeah, but it's still there.
I know. Okay. Inactive operators.
So this is Oliver's stuff, but now working with DSolve basically.
So this is the operators introduced by Oliver. For modeling of PDEs.
Mm-hmm.
We often use them in an active form.
Yes.
And so they are now being parsed and correctly interpreted in the symbolic DSolve as well as in NDSolve. Doesn't mean we can solve all of it at all. It means that in the cases where it can be solved, it will.
Okay, so in other words, if I put in a simple heat conduction equation thing of the kind that, actual humans are expected to solve,
yes.
We should be able to do it here.
Yeah, exactly.
I wish we had units in these in time.
Yes.
Okay. So what is this? What are you showing here? Some random. That has numbers in it.
That's a solution.
I can see that, but why does DSolve value have 3.14? Why is it not pi?
Because there's some
the input seems to have approximate numbers in it to begin with.
Yeah.
So why is this different from what Oliver was showing before? What's the symbolic part of it?
It's the formula.
Oh, I see. So there's an undetermined coefficient here. There's a constant of integration.
Yeah, but also Oliver's way of solving is called finite element. It uses a completely different scheme of solving. It doesn't give you.
I understand. It doesn't give you any symbolic result. I realize that.
Yes.
Although this particular symbolic result involves an undetermined coefficient.
Yes, it has an infinite sum.
Yeah.
Oh, that was a sum. I didn't even know.
Yeah, it's an inactive sum. Yes, basically.
But so I could use this if I wanted to. And if I took that thing, and maybe you did that already, but if I took that thing, it looks rather ugly there, in traditional form, I don't know why it was in traditional form, but I mean, so if I recompute this, so I just like to change that to I'm going to take that to be x equals 1. And then I'm going to take that to be y equals 2 for no particularly good reason. Okay, so then I have, so now boundary conditions, and I solve this.
Right. It might take a bit of time, so it's a hard equation to solve. That's okay. It should still finish up.
Well, that solved immediately, but I don't want to do any choppery.
Right.
No chopping, no traditional form, no, I just want, I'm no sleight of hand here. The capital T bothers me. Okay, what happened there?
Well, it's returned immediately unable to solve the problem for some reason.
I should note that. It should have worked. TXY.
But why did it? Well, I can send this to you, but I mean, why?
Oh, what's capital T? It's oh, that's what you're solving for.
No, there's the independent variable.
Oh, Sandra is pointing out the rectangle has to be bigger. Outside that.
Thanks.
Right.
Okay. All right. So let's go down here. So let's reevaluate all this stuff.
And we need to give the conditions on the boundary of the rectangle. So the rectangle has to kind of match the boundary conditions.
How ugly. I mean, in other words, it's annoying that would be something where you couldn't explicitly ask for the boundary of this object. In other words, are you giving the boundary? Okay, can somebody tell me what the boundary condition should be?
So your dirichlet condition has to be on the same.
Okay, so x equals, is this, I forget, rectangle goes from x, y, so that equals x like this, right? Y equals 1 there, right?
Yeah.
And now we got a Neumann condition at y equals 0.
Yeah, not start to compute, sorry. So we need to have the Dirichlet conditions given exactly for the problem to be well posed. Otherwise, you don't have a well posed problem. And this is, I mean, it's pretty hard. It has to do some integration, but it should finish up. And you might get some pretty big
so
numbers.
my next comment is, I would love to have a progress indicator here.
Okay.
What would it say?
We're getting to that. We haven't really introduced them yet in symbolic computation, but we're gearing up to introduce them in many places, actually.
Okay, well, that was pretty impressive. Now, so if I take that function and I say, let's say 0.5, 0.4, 0.5. Hello, why didn't that evaluate?
Because it's an inactive sum.
So now we need, if you activate the problem, it's going to try symbolic evaluation, which is not going very successful. So you need a finite sum to get something useful out of it. I mean, these sums are essentially impossible to evaluate symbolically. They are formal results, and you need to replace infinity by something to get a meaningful result.
Right.
Then we need some functions that do that.
Well,
why did this produce inactive results? Well, there was nothing inactive in the input.
Because if you don't do that, then you get back a sum.
I know, but how did
we really want to do that. We want to produce inactive integrals and inactive sums. But I agree with you, Stephen. We need a workflow that makes it easy to get sort of finite results under some level of control.
Yes.
Right.
I mean, to me, this is the wrong name. D-solve value, if you're trying to get an inactivated result, there should be something in the D-solve value that says, give me an inactivated result. Otherwise, I expect
if we don't do that, Stephen, we will be the slowest system on the planet.
Yes.
Okay, guaranteed. Guaranteed. Okay. For no good reason, just self-inflicted wounds. For no good reason. Just completely self-inflicted.
Right. And Stephen, Stephen, right? Well, people, right, when they're solving PDEs, right, they do expect to see the sum of the projection onto the eigensystem, onto the eigenbasis.
I know.
So
I don't think it's consistent, though, because there are other cases with D-solve value where it does not give inactive results, where it just gives the final result.
Right, but that's also judgment call. I mean,
but that's when there's a closed form, right?
I think that we could perhaps have an option that controls that, and the default setting should be automatic.
That's fine.
But then you could insist on it evaluating if you're one of those.
That's fine.
Okay, and
That's
you'll
fine.
just wait.
That's fine.
And that,
Now, in this case here, the problem is you've got an inactive sum,
Mhm.
but there's no way to reach in other than me editing that infinity, which would be really weird. There's no way for me to reach in. And I mean, I'm surprised that this isn't giving me some approximation. I mean, isn't it perfectly well able to deal with infinite sums?
Yeah, it is.
Yeah, n sum is not. We've tried. Okay, we've tried to replace the sum with n sum. It's not so good. I mean, in terms of quality of results, because n sum doesn't know much about oscillatory sums. That's the. I mean, we just tried last week actually to see whether we could use n sum instead of replacing the infinite.
Well, n sum is using extrapolation techniques, right, to figure out what the sum is doing.
Right.
And if the thing is oscillating like crazy, that's probably not going to. I mean, depends how you do that. I mean, if it's doing some Fourier analysis of the summand, maybe it can do it.
Yeah.
But if we're going to have lots of oscillatory sums that we really care about, we probably should be doing that. All right. So what is it doing right now?
It's trying to compute the exact.
I know, I understand that, but why is it taking it? I mean, what could be?
Because summation is undecidable.
Because the summation is very hard to.
What is it trying to do? What is it doing?
Right. So it's an infinite sum. It's going to try and a few things. It's going to first try the algorithm for trigonometric summation. Then it's going to try and do an expansion. It's going to try and do some Q-rational summation, convergence testing. So it's going to try the whole battery of a large battery of infinite sum methods where there's no hope of getting a solution at the start itself.
Okay, but so the basic point is you can't even tell me the first digit of the answer. Is that correct? I mean, that's really hard to know because it's an oscillatory function.
Right.
Is that correct? Okay.
Yes.
So for example, I'm gonna test whether you're right there.
Okay.
So let's this function.
Uh-huh.
I replace k1 with x, and you know what I'm going to do here. Oops,
No.
Why did that not work?
Because you missed a
slash
dot.
Well, okay, that would be a good reason. Okay, so now let's say plot this.
Huh?
X goes from 0 to 20, let's say.
And maybe you need a re-in plot, or
Do I need a re-in plot?
I don't think so. Not for this one. No. Should.
yeah. I'm a bit surprised why we're not actually seeing anything. Yep,
Well,
apparently you
turns out
do.
we need a
Okay.
re-in
Good.
plot.
Good. Yeah.
Okay, so the claim is this is an oscillatory function, and you seem to be correct about that.
Yes.
What a mess. Wow,
Right.
what a mess.
Yeah. But this is the Laplace. So it's got a combination of hyperbolics and trigs. So one of them will come from let's say the x, and the other one will come from the y. So
Okay, but so in the infinite sum,
Uh-huh.
we're going off to x equals infinity. I don't see much contribution from you saying that all that center stuff cancels out, and
yes.
we're left out with the.
Yes, that's the whole point. That on their own, each term is not that meaningful. But when you combine them, then you get that nice cancellation. And so at 40 terms, that thing you see over there is pretty close to ND solve. The plot you see down below, that's from the ND solve documentation. That one, yeah, that is exactly what the FEM method will get you.
No, I understand, but I'm asking the question here.
Yeah.
You are claiming the reason you can't do the sum is because there are tail contributions that the center has canceled out, and there are tail contributions that can, mess you up. Is that correct?
We are not doing numerical summation. If you're doing numerical, the tails matter. When you're doing symbolic, you need to be able to do the whole sum. And you can see that you have a combination of hyperbolics and trigs. There's no hope of those working inside sum. That's the point.
No, I understand, but Devendra, if I try to compute this,
Uh-huh.
Just numerically, right?
Yes.
This is obviously a complicated, messy thing, right?
Yes.
It looks like it might be, there's a big contribution from these guys here, right? I can see that perfectly well, right? There's no big contribution from these tails here.
Yes.
Right? So my question is, why isn't that something that sum is capable of dealing with?
it can be sum that does it. It'll be n sum that would do it. I mean, how unless you want us to return an
No,
approximation.
no, no. I understand. I understand. But in this case, this would be if I
don't see
say
why n sum wouldn't work.
would not work.
I mean, it should work.
Yeah, well, I would think it would work. I mean, was it from 0 to infinity?
Yeah.
Yes, it was from 1 to infinity. Okay, so let's just try n sum of that. Okay, so it's got a tiny complex part. So let's take n sum as a function of x max. Okay, let's just plot that. X max goes from, let's say, 5 to 30.
X max.
Thank you.
Oh, so you're saying, yeah, maybe in this case it might actually, yeah. Okay, so what happened? I think you might need to do
Oh.
well.
No,
Yeah.
the problem is that has
Floor
to
or
be
something.
floor, yeah.
I don't know why that would complain about that, to be honest. Should.
Oh, you know that this is going to crazify the let's do this. Let's just make a table of that
Right.
with x max there. My gosh, why is this taking forever? What is this doing? What on earth is this doing?
Unfortunately, n sum, you might, if it did verify convergence goes to false, you might be more lucky.
I'm not looking for luck. I'm looking for the
No,
result.
I'm just saying that then it won't do the convergence testing and sum. Otherwise, it's going to take time to do the convergence testing as well. And by default, it'll have about 25 terms which it'll pick up to do the approximation.
Okay,
But
so if I
it's
take
a finite sum, why does it need convergence testing?
yeah, I mean here I could just use sum actually.
Exactly, yeah. That's what we are doing effectively. That's exactly what we are doing.
Oh, this is exciting. I haven't seen this new what the heck is that?
Yeah.
There's still an x in %47. It's %47, not the thing. Oh wait, we're summing over x. We have variable
Well, let's
confusion.
just I don't know. Let's put that there. Then there won't be any confusion. Oh,
There
look
you
at that.
That worked.
Okay, now
Yeah.
look at what I see.
Yes.
Look at that. Isn't that beautiful? Isn't that, I mean, if I say, you know, okay, that is not a difficult piece of convergence.
Well, yeah, but keep in mind that we have to use what's available. So if I call n sum, you can see I don't have any hope of getting a good result quickly in general. So my best bet is to use a finite sum like you're doing over here. That's exactly what we do when we approximate. So when we plot things, we first replace infinity by some large limit, like
but not you by hand. We're
Right.
talking about something that automatically does that, because in this case, we can plainly see, and you know, a little dash of machine learning would probably help it even further, that this thing has, you know, this thing is dead. It's flattened out, right?
Yes.
You don't, you know, this was a really elementary thing for me to do, to just take 10 terms or something and find out that it's, you know, completely flattened out. We didn't need to waste a huge amount of time. We could have just computed those 10 terms, compute 10 terms and 20 terms and see if they're the same.
Right.
That's a
No,
good
I mean, we
start.
couldn't
Well,
return
right, but-
that from, we couldn't return that from
Right.
these
So,
holes.
so
Exactly.
right. You got it for 10 terms for a particular value of x and y.
Absolutely, absolutely. But that, what I'm saying is, I don't understand why n sum in this case was just dead in the water. What is it doing? Why couldn't n sum figure this out?
I don't know. I mean,
True.
why don't you
we'll
try n sum
try it
again?
again, because maybe it was the same variable issue.
Yeah.
All right, okay.
What's the same variable issue, maybe?
Okay, well, let's try it. So n sum, you're saying I take this. So what I want to look at is n sum goes up to infinity here. We're waiting.
Right. And you could try verify convergence goes to false to, like I said, that's what people do when they want to speed things up, because it's going to do some convergence testing on its own. That might work. I don't look after n sum, but that would be my guess, and that sometimes that helps.
Right. It could also be well, there are issues with our n family of functions, you know, the older ones. So
I think this one was trying to be too clever for its own good.
yeah, that does seem like it should be able to handle it better.
I mean, it's such a smooth looking function here. Right? This is well, this is dead. Could somebody mute themselves if they're yeah, look at that thing. Okay, you got to look at nsum and do some obvious things. I think nsum was just trying to be too, you know, it's using some crazy algorithm with extrapolation that it absolutely doesn't need in this case, and where it can't prove extrapolation, and so what?
Yeah, there's a whole family of things that need to be done for nsum, but this is not the team, first of all.
No, I understand, but it's kind of torpedoing your otherwise nice results here, and you're building a whole bunch of, you know, crazy sort of hackery around it to avoid the fact that that isn't working. I mean, it should be the case that if I just say n of this, it just works.
Well, I'm not sure. Well, okay, I agree that n of it should work, but I mean, I don't think we want to replace that sum with n sum.
No, we don't. We absolutely don't. Look, I think that having automatic for the inactivation thing makes sense for desolve value. And then I think, you know, figuring out how to make n of that work properly is the other part of that story. When will we be able to do my favorite nonlinear?
What's your favorite?
Sandra is asking, will nsum with infinity still take an infinite time? No, that's the whole point. I mean, that's, you know, nsum is, that's why nsum is doing clever things. It's trying to basically find a fit to the function that allows it to transform the thing so that it becomes a finitely doable sum, or it's using some kind of oh gosh, what is that formula? The conversion. What's that?
Euler-Maclaurin? No.
No. The formula that allows you to replace Poisson summation formula for replacing sums with integrals and so on.
Yeah. But with Moylan, we started a whole program to update all these functions, but then he moved into marketing. So that's not moved since then. We have there's a whole range of things that nsum doesn't know about, and it's not, which we've run into. It's the same as the old n integrate, but new n integrate is very capable in comparison.
Can you use some of the same technology for nsum?
Kind of. It's not as big an overlap as you think. But one of the class of methods that we really needed to use more of are these convergence accelerators, nonlinear convergence accelerators.
Yeah, for sure. I mean, that's basically transforming variables.
Yes, but we need to allocate resources, otherwise it won't get done.
Okay. What is this doing? Nonlinear first order PDEs. It is what it is.
Yeah, so that's a complete integral from desolve. Sharper's method is slightly more systematic. It does essentially the method of characteristics for first order PDEs, and this works in the case of 2 variables, and there's Jacobi in the case of 3 variables. So these are kind of improvements to strengthen our nonlinear first order PDE solver.
Mm-hmm. Well, fair enough, except that I don't know. Okay, explain the value of this, given that you can't actually solve the general nonlinear PDE.
Yeah. So for each set of parameter values, you have a solution. Then if you take a family of those, you can get envelope solutions, which are, you know, the limiting case of any family. Like you got the second constant C2 express the family of the function of C1. Then you get an envelope construction, like a Huygens construction, and that's another solution. So although it looks very simple, this can be used to build up a general solution for the PDE. So it's a constructive way of building solutions for the PD. That's the way it's used in things
Okay,
like.
but the thing I don't understand is, I would think that there are names like a general solution, there are these different named kinds of solutions
Right.
for nonlinear PDEs.
Yes.
Why can't I just ask for one of those types of solutions? Why isn't there a way of asking dsolve to give me, the general solution, a special solution, whatever else, rather than just you type it in and you get some random solution that it happens to be able to give?
Right, because I think the chance of getting a general solution for nonlinear PD is almost zero. The linear case is very different, where you essentially only have complete solutions.
Okay, but what are the named incomplete solutions, so to speak? Aren't there names for different types of incomplete solutions?
Well, one kind of incomplete is where you only have like one solution which doesn't have any parameters in it. Those are not good for us because that means we can't reuse them anywhere else in dsolve. I mean, they're dead. These ones are the only family which we have improved because these are kind of reliable. They have.
And so what's the name for this family?
A complete integral. It says find a complete integral.
Well, that's what I thought, right? But that's why I'm saying
there are other ones too, solitary wave solutions.
Well, those are not for first order, but mostly for
the KdV equations or something. But right. But the point I'm making is, I would be much more convinced if it says find the complete integral for this, differential equation, than solve the equation where I know it's just a shot in the dark, because most nonlinear PDEs are just hopeless, right? So why don't we have a thing called complete integral that will compute that for a different, for a PDE, and another one called, I don't know, if it makes sense to say soliton solution. I'm not sure if that's a well-defined thing.
Well, solitary wave are not soliton. I mean, they build up solitons, but
fair enough. Okay, right. The solitary wave is the building block, the tanh or something for the KdV equation, or whatever it is, if I remember.
Right.
Yeah.
So why don't we have that?
Right. So you want new functions which do that? Sorry. Do you want new?
Yes.
Functions?
Either that or possibly an argument to dsolve. But I think new functions make more sense, because you're signing up for something you can actually deliver then, rather than saying, dsolve can do whatever it feels like for a nonlinear PDE. It's not going to get very far with it.
Right. So historically, that's how we did it. In version 3, we had a complete integral function inside a package, which then got baked into dsolve because we didn't want a package.
Okay, well, so then maybe we need to make it its own function now.
Yeah,
maybe it's powerful enough that it actually makes sense. I mean, it's no good having complete integral and then it only works in 2 cases.
No, this one is actually, that's the whole point. That we've tested on COM case, we've tested on lots of sources. So it's now pretty powerful. In fact, that's the other thing we didn't talk about, the monograph on PDs, which, actually says exactly what we have in this area. And we have a lot. I did a lot of testing for version 6.0 actually. And then since then we've been doing a bit, but this is getting more complete now with the Sharpit and Jacobi methods. So I think I have no doubt.
So let's plan on a function called complete integral.
Sure, definitely. Done.
I gather Adam just joined. I'm really late for something else, so I'm not sure we're going to be able to cover this. But what was the question for Adam?
It was zero recognition for root objects.
They are never zero. So we try to recognize zero before we solve the equations. So no coordinates of those root objects will ever be zero.
Okay, but what about equality testing? In other words, can I end up with 2 root objects which are in fact the same number, but which are sufficiently differently presented that equal can't determine them to be equal?
Yes, of course. Which is true for other number representations that we already have. We can have explicit representations of X-block numbers that are the same, but we cannot show that they are equal.
Is that true for polynomials or only for our more extended?
For algebraic numbers, we can in principle always decide that whether they are equal if they are algebraic numbers written as root objects or radicals. If we go outside that, like we add X-block or other elementary functions, already we cannot prove that 2 things are equal.
Right, and it's not just our fault. It just happens. It's basic. Does that hit undecidability immediately with exp and log? It may not be known.
may not be known. Yeah.
Right.
I think if we go too complex, then we would be able to encode a Diophantine equations in terms of some explode combination.
I don't think you need complex. I think you just need trigs.
Oh yeah, yeah. Actually, we don't. Yeah, we just need trigs, right? We cannot trigs and pi, and we can encode integers. Once we can encode integers, we can encode the undecidable Diophantine equation, and then we can't tell whether it's 0 or not.
Right. Okay, but as a practical matter, okay. So the question really is, if I type, root object equals equal root object.
Mm-hmm.
There are then three cases.
Three cases, yes.
We know they're not equal. We know they're equal, and we don't know either way.
Yes.
Okay, and you handle those three cases.
Yes, so it's the standard evaluation of equal. So it tries numerically, then it tries some symbolic transformation. Otherwise, it comes back unevaluated.
Okay, fine. And how common is it for one to end up with the same algebraic number, but it is not recognizably the same?
The same, you mean the same non-algebraic number, right? The algebraic.
No, I'm sorry. Okay, the same transcendental root. Yes.
I don't think you would do it. It's not likely to happen.
Do you have an example?
By chance. Not ready one, but it's easy to construct. If you want to construct one, it's pretty easy. Just take some functions that are not obviously the same, but they are the same, and then take the same root of those functions.
Okay, but so the point is, there's no full simplify that's being done on the function in the first argument of the root object.
Right, and full
even if there was, it wouldn't.
Full simplify is not canonical, so it wouldn't help.
Right.
So there is actually full simplify for those root objects where we try to call reduce and get the explicit solutions. But again, it may or may not work.
Fair enough. I mean, that's life. There's nothing we can do about that. It's just the way mathematics works. Okay, I think that was the answer we needed. Okay, there's a question here. You need to know if the number is algebraic, or does the program decide if the number is algebraic? Well, within reason, we decide, but if you ask whether pi to the e is algebraic, I doubt anybody knows.
Right.
Or
we cannot recognize 0. So 0 in particular is algebraic.
Yeah. What if square root of 2 to the square? Somebody asks about square root of 2 to the square root of 2, because that one is known.
What's the answer for that one?
I believe the answer is yes.
That it's algebraic?
Or is it that it's no?
I bet.
I don't remember. I'm trying to remember. I just remember. I just remember this was related to one of the Hilbert problems that was eventually solved.
Yes, that's right. I remember that too.
And so the answer is known.
I wonder if we know it.
Yeah.
Adam, how do I ask it for the square?
Element algebraics. If there is a criterion that will do this, then, or if we know about one, then it will work.
Oh, it says false.
Okay, so it's
okay. So
right.
that,
so it must be transcendent. Yeah.
So that there is a criterion that does that. So we have some of them implemented.
Right. Cool. Okay, good stuff. Anything else here? I need to run along. All right. Thanks, guys.
Thank you.
Thanks to folks on the live stream. See you another time.